Welcome back to The Explainer. Today, we're looking at megastructures. We're talking billion-dollar industrial plants and massive, towering vertical vessels. But we actually aren't going to focus on the giant machines themselves. We're looking at the tiny details that hold them all together. The invisible foundation, the anchor bolts. Because a single mistake here, it literally means catastrophic failure. So let's uncover the butterfly effect of construction. Okay, let's dive into this. Imagine you're standing in a massive chemical plant. You've got this pressure vessel weighing well over 1,000 tons, standing over 100 feet tall, just reaching into the sky. Where does the power to support hundreds of tons actually come from? Well, it doesn't come from magic, right? It comes from these incredibly small, seemingly simple steel components that are holding the whole thing down to the concrete. Think of a giant, towering redwood tree. No matter how absolutely massive the trunk is, it needs deep, incredibly strong roots to survive a major storm. In plant construction, heavy anchor bolts are those roots. Without these pristine fasteners acting as the root system, that multi-million-dollar equipment will literally tip over and fail. So, what exactly are we dealing with? Let's define it. An anchor bolt is a heavy-duty steel fastener that is deeply embedded into the concrete foundation. It acts as the critical root system that firmly secures massive industrial equipment in place. And today, we are hyper-focusing on one absolutely critical task: thoroughly checking the condition of these bolts before any equipment is ever even installed. There's this old universal engineering truth. Preparation is 90% of the work. And in the plant construction industry, thorough preparation is quite literally everything. We don't rely on luck. We rely on rigorous, uncompromising pre-checks. If the foundation isn't absolutely perfect, the machine cannot be installed. It's really that simple. Proper preparation prevents massive disasters. Now, what's really interesting about this procedure is the strict four-step framework for Section 2.2.4, the anchor bolt condition check. We have to execute these perfectly. Step 1, cleaning and contamination. Step 2, thread condition. Step 3, the verticality check. And Step 4, the projection length. All right. Let's kick things off with steps 1 and 2, threads and contamination. So these bolts are poured into the concrete long before the actual machine arrives on site. And that waiting period, that is a major danger zone. A healthy bolt will have clean threads, it's well greased and perfectly protected. But a defective bolt, it's completely covered in concrete splatter, rusted, and the threads are damaged. Why does this happen? Because during the civil construction phase, wet concrete splatters everywhere. If you don't protect the bolts, that splatter dries and hardens directly onto the steel threads. And the danger here is incredibly real. Even a tiny amount of hardened concrete is a total nightmare. It blocks the heavy nuts from tightening down smoothly. If a worker gets frustrated and tries forcing a nut over that concrete splatter, it completely destroys the bolt's threads. And once those threads are stripped, the structural integrity is entirely compromised. The bolt simply can't hold the machine down anymore. Fixing this means you literally have to chip out the concrete and replace the bolt, which causes massive, unbelievably expensive project delays. Moving right along, that brings us to step 3, the verticality check. So the crucial point is that this is where we shift our focus to absolute straightness. In high-level plant construction, tolerances are microscopic. We often measure allowable deviation in fractions of a millimeter. For some highly sensitive rotating equipment, alignment tolerances can be as tight as 0.2 millimeters. To put that into perspective, that's about the thickness of 2 sheets of standard paper. There is absolutely no room for error. Picture this. You're a junior engineer on site. You've got a massive crane suspended high in the air, and it's carefully lowering a 50-ton heavy-duty pump. The tension is high. But as it gets close, you suddenly realize one single anchor bolt is leaning just a tiny bit. Just a fraction of an inch off. The holes on the pump base simply will not line up with the bolts. The installation stops cold right there. If an anchor bolt is even slightly bent, the multi-ton equipment simply will not slide into place. And finally, we arrive at step 4, the projection length. And this brilliantly illustrates what we call the Goldilocks zone in engineering. Projection length is simply the amount of the bolt that sticks up out of the concrete. It has to be just right. If the bolt is too short, you physically cannot thread the massive nut on top to safely secure the machine. But if it's too long, it might actually crash into the bottom of the equipment base or even interfere with moving parts on a rotating motor. You have to verify this exact length before the crane ever lifts the machine off the ground. So, how do we prevent all these headaches? Here's the actionable, industry-standard advice to keep things running smoothly. First, apply heavy anti-rust grease immediately after the civil works are done. Don't wait around. Next, install heavy-duty thread protection caps right over the tops. You should also wrap any exposed sections completely to block that wet concrete splatter we talked about. And lastly, conduct thorough visual inspections long prior to the equipment ever arriving on site. Let's move on and see how this all builds together in the zoom out, the butterfly effect. Up until now, we've focused on tiny steel threads and literal millimeters of straightness. Now, let's step back and look at the plant facility as a whole. A single damaged thread can hold a billion-dollar mega plant installation. I want you to really think about that for a second. The crane is rented, the entire crew is getting paid, the schedule is incredibly tight, and all of it stops dead in its tracks because one piece of steel wasn't properly checked. Skipping Section 2.2.4 isn't just a scheduling delay. It leads to actual disaster down the line. If bad bolts are forced, the equipment won't sit perfectly flat. This causes severe equipment vibration during operation. And that vibration, it causes accelerated wear and tear on rotating machinery, tearing it apart from the inside. Over time, it can lead to catastrophic structural failure. But most importantly, it creates completely unacceptable safety hazards for the hardworking plant workers on site. So the next time you drive past a massive skyline of industrial plants, take a moment. Ask yourself, are you trusting the giant steel structures towering above you, or are you really trusting the heavily inspected tiny bolts holding it all down? Thanks for joining me for this explainer, and remember, big success always starts with the absolute smallest details. See you next time.